everyone. My name is Hongyang from Shanghai. I just arrived in the States, so there's might be some jet lag. And so my title, the title of my talk is could foundation models really resolve end-to-end auto driving? So how many guys of you vote for this? So foundation model will definitely resolve end-to-end autonomy. Okay. Really resolve or partial can resolve for the time being now. Okay, I see a few hands up, only a few. Okay, and how many of you have already come from the industry? Many hands, and the rest are from the academia. Okay, only a few from the academia. Okay, that would be great. Because I'll briefly talk about the roadmap in the research, because I'm asked to give you a deep dive or walkthrough of all the recent end-to-end autonomous driving research, especially in the academia. So my talk consists of 3 parts. So the first one is introduction to the end-to-end and the data sets, the evaluation, and also the motivation. And the second part is some recent work from the community, not only from our group. And the last part is a few challenges and closing remarks as to what's the so-called future of end-to-end autonomous driving. Because I just came back from a few test trials, especially a Chinese corporation called Huawei, and another is from Tesla, and I also test a few other products. I mean, we just sit there and to test from like the from the source destination and to the destination. So I think most of the cases in the autonomous driving nowadays are well resolved. So the only reason that we are here is that whether we can mitigate the marginal gap between the resolved part with that of the corner cases part. So the first one is introduction. This is a problem setup. As we all know, autonomous driving consists of 3 parts, where the perception is about recognize the objects, whatever in whichever form, 2D bounding box or 3D bounding box. And the prediction part is given the ego vehicle. So how could you predict the intent or trajectory in the environment of the other agents? And the third part is planning, where you have given all the preceding information, whatever is perception results or prediction results, and you're gonna plan your own trajectory in the next few frames. So we do have lots of challenges. So the first thing first, as Jimmy already mentioned, I suppose, the definition of end-to-end in our case, in today's talk, is that this is a suite of fully differentiable programs that takes raw sensor input as input, raw data, I mean, whatever camera, LiDAR, canvas data into the system, and then produce a plan or low-level control actions as output, which is shown in the red block here. So compared to the conventional modular-based design, where each module or functionality would output the direct results in whichever form you can name it, mapping results or bounding box. So in the end-to-end paradigm, so each module would feed forward the features or representations, and you only got you only got major objective functions or training loss to get back propagated through the standard deep learning optimization process. So this is the major distinction from the end-to-end compared to the modular-based design. So there are also some preliminaries. The first one is data sets and evaluation. So as I mentioned earlier, we are tasked to do the planning task, which is to perform a few waypoints or trajectories of your own ego vehicle in the next few frames. So there are some renowned data sets. The first one is nuisance. And I think all of you no nuisance, right? So the behavior or interaction, I mean, the behavior of the surrounding agents with the interaction with your own ego vehicle is realistic. It is captured from the realistic data sets. And the strategy here means once the data set is collected, you cannot modify the trajectories, right? For example, from point A to point B, as long as the data set is collected, so the trajectory is fixed. So this is called the open loop evaluation. And for the metric, which means the metric is to evaluate how well you did the trajectory prediction or other tasks, is the L2 error. And I think the other, the rest data sets like Waymo or Argos is also very famous, and it is performed in the similar way. And recently, we see the new plan data set benchmark. It consists of way larger, at least 1 magnitude of scale of the length of driving scenarios compared to the previous new things Waymo and Argos. And it is machine learning based, collected, and it is closed loop. So by closed loop, here we see, so the nexus surrounding environment is dependent on the current prediction output of your own algorithm. So in terms of evaluation, it got a various metric, whatever you can evaluate in the average displacement error, or in the collision rate, or the a comprehensive score called PDN score. So basically, it is a weighted sum of 5 or 6 evaluation metrics. So for the details, you can resort to this awesome GitHub repo. And the rest part is a synthetic generated data set. So to name a few, I think the most famous tool is DriveSim. But unfortunately, I never saw a technical report or some open source repo from DriveSim. So over the years, it's a lot of demo, and I could admit it's very fantastic. But we are from the academia, we only see the technical report as the solid evidence. So that's why we are using the Kala, which is all open source, and it can generate unlimited data because of a simulation, right? You can manipulate all the environment as assets, and it's handcrafted, and it's open, it's open looped, and it's closed. It's open source, and it's evaluated in a closed loop. So in the Kala, it has a driving score, which consists of 2 parts. The first one is how complete are your whole route finished in a given mapping town, multiplied by the infraction penalty, which if you collide with somebody else or with the environment, so you're going to be punished. So this is the data set. So why do we need a end-to-end? So over the years, I've been giving some talks as for the reasons. And as I prepared last night, I see the most straightforward motivation on this is the global optimization ability, which means this is example from a work called UniAD. And since each module is connected by the features, not the direct results. So even though here the red circle, so this is the perception results where you turn, in this case, you will turn right. But the car doesn't see there is a obstacle behind the tree. So even if the perception fails, and we can see during the feature attention feature layers in the planning part, it can also regress all the attention part. So my takeaway is that in this end-to-end paradigm or paradigm shift, you can recover from the previous module's failure, even if the perception is inferior and you didn't recognize the objects. But compared to the conventional part, which is a modular design, you cannot even ever do that, right? So I think this is the most important motivation for us to do the end-to-end. And another thing is the emergence of foundation models, which is a scaling law. So we have a massive amount of data, and you got assuming you have a lot of GPUs or infrastructure, and you can show or demonstrate strong generalization capability. But to be honest, I haven't heard any or few solid evidence to claim that we are doing the foundation model for auto driving. So I think most of the audience came from the industry. I must assume you have a lot of GPUs or data. So please, if you have these resources, you can share some public results in a technical form. And so what we are seeing here, all the way here, is that I think we are here. I mean, the green dashed line here is the end-to-end approach, but it hasn't shown very promising results or capabilities. And as I mentioned earlier, if you ever test some trial drive in this daily, like Tesla FSD in their vehicle, I think most of the cases are well resolved. So why we are sitting here, or why we are doing research, especially in academia for autonomous driving. So all the way here, we are resolving this part or this gap. So to mitigate what the non-end-to-end system cannot do, and to exhibit great generalization given the faster development from the foundation models are essential. And this part is for the efficiency. So in my previous talk, I think efficiency is the good part, but I really think this is not, especially you are deploying the large foundation models. So the FPS of foundation models is below 10, but as I know from the industry, this requirement is at least for 30 or even higher. And the only downside part, I think, for the end-to-end of driving is lack of interpretability, which I think this problem resumes in all computer vision domains. This is because due to the end-to-end neural network, you cannot explicitly explain which part takes the major responsibility. And someone may argue, okay, you have the unfair evaluation as to the open loop or other parts as for the simulation. But I think those are the challenges. Those are the challenges that can be solved, whatever from the academia or industry. So those are not the disadvantages that inherently resides in the end-to-end paradigm. So given the limited time, how much time I left? So this is a classic algorithm. It's called the transfuser. And you can see here, I will just skip that. How many times do I left? Where's that? Okay, he's nowhere. Okay, so I'll dive into this part. So this is the Unity paradigm, and I think, okay. And here, this is a little bit credit here. I must to see that given the limited time. So all the way back to the end-to-end system dates back to this project called OpenPilot. So I think this is a startup company in San Diego. I see their CTO are very active on Twitter. And we really bought their equipment and tested in Shanghai. And this back to 2 years ago. I think this is the first time that drives me to see autonomous driving can be such a simple thing to use a simple network to directly output the control signals. So if you have some effort or have more interest, I would strongly encourage you to buy some product from them and test it in your own car. Okay. This is a personal advertisement for this. Okay, and the second part is research panorama, which is I have skipped some conventional approaches, the introduction of them. So the very original end-to-end can be dated back even into before the 20s, where I think this comes from some blog from NVIDIA, or I'm not sure. So the input is even black image and relying only on the neural network, which is just 3 MLPs. and you can have a control system. And then here I omit a lot of related works here before the 2020. So here, so the y-axis is a goal. I prefer to use the word goal. You can refer to it as performance, or if you are from the industry, it indicates the MPI. If you are from the academia, it indicates some performance score on some specific benchmark. And recently, we see the UNAD and many others. For example, VAD, I really like VAD work. Is way efficient than the UNAD. So the gap or the gain from the previous work, I think, to my opinion, is a formulation which we should shift from the modular-based design to the end-to-end. And there is no scale of data. I mean, the size of the circle indicates the data scale because they are all doing on the new things, well-studied new things. And we all see from the industry, there is a hype that you can utilize different end-to-end auto-driving system. At least in China, I think literally every car company claims they have deployed the end-to-end system. I'm not sure whether this is the case in Europe or the States. So for example, I've seen the advertisement from Mobileye in CES this year, and also other Chinese corporations, just to name a few. And I think there are some concurrent work, which is Gaia and Prism, which is released yesterday, a few days ago, and also the JAD or Lingo other work. So to be honest, I think the marginal gap is the gain is really marginal because I think the data scale helps, but VLMs or LMs should do better. I could talk about this topic for the whole day, but given the time, I should first put the conclusion here. So given on the future, so what's the future? Should we fully leverage all the data given from the large amount test scenarios from the simulation or the so-called embodied AGI? So what should we do? So my takeaway or missing ingredients consists of 4 parts. The first one is the data. Everyone knows about the data, right? And the second part is this is where the university faculty or research students steps in. So we can still do a lot of technical contributions in architecture, whatever you are using the dual system, or you are using the word model, or using the video prediction, such as what they do in the Sora. And the last missing pieces is the info of platform. I'm not sure if any of you or most of you have dealt with training with hundreds of GPUs. If you are doing this, you must be much remember that the training stability is very important. And also the deployment. How could you deploy the large-scale foundation models on board? I've been asked 1,000 times, even though I came from the academia. So I think that's a major responsibility from the industry. So let's take our respective role, okay? So my take on the generalization to achieve the end-to-end autonomous driving system starts with the data. So we have the we have to collect the massive amount of data, and then we have to think about the effective action or policy learning. How could you utilize the whatever reinforcement learning or imitation learning? Here are some examples of previous work from our group or from the other groups, including the MP3 or UNAD or driver adapter. They are mainly focused on the algorithm part. And also, as the emergence of LLMs, we got interpretable causal reasoning, whatever you are utilizing the LLMs to interpret the scenarios. But for now, for the time being, as of today, I see no evident improvement given from the large language models. So one of the reasons is probably that the output of the conventional task in auto driving, whatever is planning or motion prediction, requires numeric or exact trajectory outputs, which is for the LMs is incapable at all to output the exact numeric numbers. So we were seeing a lot of LMs in the driving scenarios, right? And most 99 of them got rejected by the CVPR or by other conferences. So I think the major takeaway is that yeah, the LM doesn't express the very good results or generalization as shown in the other domains, such as the general vision domain, as it is shown. So then we got the closed loop simulation. Closed loop simulation is really important because you have to interact with the environment, right? So the trajectory is not fixed. As long as the algorithm has some output, the environment has to shift according to your algorithm. So in such case, the end-to-end auto driving can be deployed with zero gap to the production. Otherwise, it's only a prototype stage. And then we got, once you have the closed loop simulation, you have the demo collection where you can collect a lot of safety critical scenarios, and you can design reward or other feedback depending on your algorithm design, whichever is imitation learning or RL. And then it comes to the safety deployment. Okay, so I'll just walk through a few works. If you are taking it seriously, there is a very good survey paper written by Li Chen. I'm not sure if he's here or not. So we have summarized all the detailed work and grouped them into together. And we draw the color driving score here. And so if you are seriously want to work on the end-to-end auto driving, I would highly recommend it. So I will also skip this part. I will be a little bit lengthy here. So we have a poster on Thursday. I'm not sure. So this part is as I said earlier, right? We are in the age of foundation models. So how could you utilize all the YouTube data, or how could you express good generalization ability? So this is the motivation of the GenAD work, where we utilize all the internet data from the YouTube driving cases. So as you guys can see here, those are all the driver videos in the front view. So it has seen almost all the globe in all the continents. So using this paradigm, you can for sure using the self-supervised learning or unsupervised learning to see the potential of creating a foundation model in auto driving yourself and see how it performs in the downstream tasks such as planning. And the other work is, I will skip that. We really got a lot of the slides. And the next part is the VISTA project. So I really like this project. It's recently released on arXiv. And so given the VISTA work, the GenAD work, we have limited data on new things, or we have the representation capability, which has a very small scale of resolution in auto driving. And also the control flexibility, which means previous work using only a single modality or compatible with planning algorithms. So in this work, we have built on the GenAD dataset, which consists of more than nearly 2,000 hours of driving data. And then we have the resolution is much higher compared to previous GenAD DriveGAN or other works. And also we have more control flexibility. But yet again, I think this is a very marginal work because we are still facing the problem. Okay, you have the foundation model for driving, then what? So how can you apply the foundation model, how can you drive like a human driver, like we are using these foundation models, not to mention the deployment thing. How can you drive smoothly and in some out of nowhere cases or in some corner cases, you can generalize or right? This is a core capability of foundation models. But for the time being here, I haven't seen any work that has claimed such capability. So most of the work just stop here, which generates the very fancy Sora version in the driving cases. So this is where our university students or research scholars could invest lots of time to work on. So this slide shows a few bits of VISTA, which exhibits high fidelity in the future prediction or continuous long horizon rollout. I knew this is nothing new given the emergence of Sora, but in the driving, at least in the driving domain, I've never seen such high resolution or long horizon. I think it's 50 seconds or 20 seconds, I'm not sure. But again, given the amazing performance of Sora, someone say this is no big deal, but please show your work, okay? And this is a drill shot action controllability. I'll skip this part. It's just more better performance. Okay, so this is the last part. I'm sorry for the lengthy talk. And this part, I really want to see the challenges or closing remarks of what's the future or what's next in the auto driving. Because nowadays I'm often asked, does it make sense to do research in the university? So my guess is, so if you are doing the perception or prediction on conventional benchmarks, no offense, is probably that. I mean, what's the big deal of improving 2% of mean AP on new things? Let the task be resolved by the computer vision domains. I mean, there is a whole bunch of people doing object detection in this whole CVPR, right? The reason of all of you come here to this room is to resolve real world problems for auto driving. We are a applied science domain, right? So I really think there's no big deal to work on this. So please stop doing some research on new things. But no offense, Holger, we are very close friends. He just visited us in Shanghai, but no offense to new things at all. I mean, this is a great work. Okay. And previous hype indicates last year we got the end-to-end trending topics. Everyone talks about it. And nowadays we have the new baby called word model, dual system, and other neural rendering techniques, right? So for the academia, I don't have too much results. Is there any impact research left? So my opinion is maybe in occupancy or in mapping or in motion prediction, I don't know. Maybe there is. But for the industry, we often heard we have lots of GPUs, millions of driving data, but we cannot get access to it. So could we beat Tesla or other winning corporations, no offense to other corporations, and achieve L4 once for all using end-to-end? So my answer is definitely not. And because there are just so many unresolved challenges. So if there is only one page of takeaway in this talk today, it's going to be next one, this one. So I have at least several dimensions in terms of data. So we need high quality or large scale data. So this is just a rough division of research and engineering. I'm not leading to either part, okay? So for the academia, I think we need some research, especially using neural rendering, whatever Gaussian splatting. We can see lots of amazing work from recent CVPR or CGraph to generate high fidelity or controllable simulation as the word engine to interact with the environment. So we see some counterparts in previous year. So the very exemplar is color, but it doesn't do well, right? Everyone knows that. But I haven't seen any well-popular platform or open source project than color. So I think doing this part is really impactful. And also for the engineering part, everyone knows that is a scalability collection. So recently I heard this book and I have checked some chapters in this book. It's called Human in the Loop, Machine Learning. I would strongly recommend you guys to have a look. So for now, I would say we would, in order to achieve the foundation model, we need at least 10,000 of hours. Given your reference, new things is only 5 hours. And 80% of them are just going straight scenarios, okay? So do not report any me AP on new things to me or to some conference again. We just need to have too many archival papers each month, right? And for this CVPR is, okay, let's skip for that. And we can see that I just take this photo from the Twitter. This is a reference on the FSD. So this is the unit per billion of miles. So after the emergence of V12, which utilized the end-to-end, according to them, right? So their data just blooms like exponentially. So we really need a lot of data to achieve this. But this is not the responsibility for one single corporation, but instead it does need a reunion from across countries or across many efforts from different parties, right? So the second part is the algorithm or methodology part. I could also elaborate or explain in many hours. So for like given the word model or video generation, we can do, so these are the techniques or the tools. This is why I put in a smaller fonts. So nowadays, many people just say word model is the only solution to all of that stuff. But in my opinion, it's just a tool. And the red part is the goal or the task. We need to achieve the closed loop feedback or to achieve the long horizon planning. And also for the engineering part is the efficient, which is the deployment, which is a forever topic that we are going to discuss. And to achieve this, the tool should be the dual system as to system 1, system 2, or model compression or whatever novelty is going to be there in the perception module. And also some people might see in the future, is it solely based on the end-to-end or solely based on the modular-based design? I would say it's not a dichotomy. It's not a yes or no. I would say it's an explicit design with explicit design, whichever something like in the UniAD where you have the perception, but it's still in an end-to-end system. Okay, so for this, I would strongly recommend you could resort to this embodied AI survey paper. I rarely recommend papers nowadays, but this is a really good paper that you can reference to. I draw many insights from this paper. I think this is from the Google DeepMind team, but it's another team. Okay, and the last part is the compute and infra. Surprisingly, I see just a few discussions in this conference to discuss about this, especially we are doing the autonomous driving research. If you're doing the foundation model, I think there are just, you need many GPUs, okay, for the university or not. And this is not indicating the whole group. I mean, for one project. So if you are doing the GenAD or Prisma, I'm not sure Prisma use, I'm even not sure this is secret or not. But for me, I think if you are seriously doing the foundation model for autonomous driving, at least 50 or so GPUs per project is needed. And if you are staying in the industry, I think at least 1,000. Yes, I think so. And the stability or how to guarantee faster I/O or other hardware issues are also very critical. Okay, so we have switched the research paradigm. So a few years ago, people might think you might only focus on the novelty or algorithm technical contribution, but as the large foundation models, I think all the people in this room would agree that data and also the infrastructure also matters way better than the technical part. So again, this is a very brief challenges. And for more details, I would strongly recommend the survey paper that we wrote a few months ago. So it has more details on that. And finally, the task or the goal should be the same, whichever you are from the academia or the industry. That is to achieve the driving comfort or experience considered, at least consider in your research. Okay, so this is my opinion on that. So the final of the final is to how to achieve this AGI goal, this climbing to the Mars, utilizing lots of tools, whatever you are using, LLMs or with models or whatever. So data as word engine, as I mentioned earlier, and algorithm, you can do a whole bunch of things here, whatever is on each topic. And info and platform and deployment. I think those are all very important ingredients to achieve the end-to-end auto-driving. So with all that, thanks for my team. And a lot of guys have just arrived in this CVPR, and they are all the author of the retrospective work, and you can say hi to them. Okay, that's all for my talk. Thank you.
I think we have time for maybe 1 or 2 questions. I see the first hand was there at the back. Great timing.
I'm from like software ability software analysis domain, and we use to end-to-end big models that are interesting. Because in engineering, there is also the complexity of the real world that we always implementation. And one big reason for this is debugging. If you observe a bug in the system, you can trace in the whole component,
yes,
debug it, fix it.
Yes.
These huge end-to-end models which are essentially.
Yes.
Repeat the question.
So the question is, how can you interpret or track all the bugs given some system in an end-to-end sense? So unfortunately, this is the very true downside part or the disadvantage part of the end-to-end auto-driving. Because if you are using a modular-based design, you can easily track which part, the recognition or the prediction, whatever. So this is where, there is a workaround for now, is to have a explicit design where you have intermediate losses or intermediate outputs. And when the planning or the vehicle suddenly collides with the road, and you can see the intermediate results of the perception results from the network to see whether or not it fails or not. But it's still an intermediate solution for tracking the bugs. Okay.
One more question and then.
Yes. Again, thanks for the nice presentation. If we look at the future of the end-to-end solution, and let's say it is a system of networks of differentiable methods. And if we then zoom in on the first part, the perception part.
Yeah.
Do you think in the future computer vision tasks such as a video panoptic segmentation or other dense prediction tasks, will they still be relevant as a method to initialize that perception module or as a form of deep supervision, or in the future we don't need these computer vision tasks anymore?
I would not go that extreme,
okay.
But my bet on this is yes, do not do segmentation or tracking on the driving again, because OpenAI or other expertise from their part can do it very well, and then you can utilize the VLMs to fine-tune on the auto driving. I mean, the segmentation, whatever the task, right?
So all that research at CVPR is not that relevant, at least not for autonomous driving.
Yeah, especially given the large scale of data, and you can verify the scaling law, etc. thing, right? Right, it's that's my personal view, right? Do not propagate that.
Oh, it sounds sounds sensible.
Okay, sure.
All right, thank you very much. Let's thank our speaker as well.